Hey guys, these notes are going to go over the historical development of the periodic table. So go ahead and pull that note sheet out, and we're just going to step through it like we always do. So here we go. So since we've been able to isolate pure substances, scientists have figured out that some elements have very similar physical and chemical properties. This just means that they behave similarly to each other, and sometimes they even look like each other. So again, scientists have known since they've been able to isolate pure elements that some elements have very similar physical and chemical properties. So here's some examples. All of these elements pictured are types of metals, the ones up here: lithium, sodium, and potassium. They all have this kind of shimmery, silver, grayish appearance, and they're all really, really soft metals. Like you could literally cut them with like a butter knife. And if you put them in water, they kind of explode, like this picture right here is showing you. So some very common physical properties of lithium, sodium, and potassium would be that they're all silver gray and they're soft. All right, that's part two. That's question two, or question two on your notes. A chemical property of all three of these elements, lithium, sodium, and potassium, would be that they react violently with water. Okay, so their common physical properties are they are silver gray and they're soft. Their chemical property that's similar is that they react violently with water. One of the things we can figure out about an element is its atomic mass. Another name for atomic mass is atomic weight. So again, another name for atomic mass is atomic weight. And what some of our earliest chemists, who are scientists that study chemistry, noticed is that the atomic weights of elements that have similar physical and chemical properties pretty much show that they're related. Okay? So at the time, chemists only knew of about 60 elements or so. But what they kind of noticed is that the similar elements seem to come in groups of three or sets of three, which we call triads. So groups of three similar elements are called triads. So early scientists noticed that when they looked at a group of three elements, the average mass of the elements always seemed really close to whatever the middle element was. So what was significant about the average atomic mass of similar elements? That the average mass was always very close to the middle element. And this became known as the law of triads. And it pretty much meant, this law of triads meant that elements were related to each other at the atomic level. So it meant that their atoms were very similar. So what did the law of triads imply? It implied that elements of that triad were related at the atomic level. So as more and more elements were discovered, scientists started to try putting these elements in groups or lists or patterns. So again, once they realized that they were coming up with quite a few elements and they were some kind of order to them, they tried to find the pattern to how the elements fit together. Okay, so they started looking for the pattern within the elements. So one of the first scientists that tried to come up with a particular pattern was a scientist by the name of John Newlands, this guy right here, and he was the first to kind of present his idea of how he thought these elements went together and how he figured they were related to each other. So he noticed that if you place them in a table and you put them in order of increasing atomic masses, then there was a pattern of similarity that repeated every 8th element. So again, he noticed, that if you put them in a table and you arranged them by increasing atomic mass, there was a similarity repeated every 8th element. So Newland called this pattern of every 8th element being similar the law of octaves, because it reminded him of a musical scale. So again, he called this the law of octaves. Unfortunately for Newland, his idea wasn't taken very seriously. And part of the issue is that there were a lot of flaws within his table. So if you look up here, the ones that are circled, those are the main elements that we have a problem with. So remember us talking about the iron triad earlier? Well, we would think that those elements would be in the same column. They go together. But when Newland did his table, they were all separated, which didn't make any kind of sense. So one of the reasons that it wasn't taken seriously is because his table really just didn't make any sense. Now it turns out, after the fact, that his idea did kind of work, but it only worked for the elements 3 through 18. Now, all of these elements were not discovered when Newland put his table together, so that's one of the main reasons that it wasn't completely correct. So were all of the elements discovered in John Newland's time? No, they weren't. So the guy who really came up with the periodic table was a Russian chemist named Dmitry Mendeleev. And he's the one that kind of came up with what we're kind of familiar with some modifications. He still kind of put things in groups of 8, but he understood that a lot of elements were missing. So he purposely left gaps in his periodic table where he thought these elements belonged. And this helped his groups to stay more aligned, more where they should go. So again, Mendeleev was the first person to come up with the real, as close to the periodic table as we know it. And even though he kept things in groups of 8, he realized that there were elements that were not discovered. So what he did was he placed gaps, he left spaces where he thought those elements should go. And by placing those spaces, when those elements were found, they could just kind of be penciled in. So it helped to keep his groups more aligned. So with the gaps that he had left, Mendel started trying to predict what some of these undiscovered elements would be like. And for the most part, he got it, almost spot on. A good example is germanium. When that one was found, shortly after he had already put together this periodic table, the properties that he had predicted were pretty much identical to the properties that the actual element had. And this is kind of how Mendeleev validated his periodic table. He said, hey, I'm leaving these spaces because I know something goes here. And the thing that goes here is going to behave a lot like the things around it. And in truth and in fact, that's exactly what happened. So it kind of helped people to believe that he knew what he was talking about. So for many years, most of our chemists were using the atomic mass of an element to place it in a specific order. But every now and again, you'd have a group of elements that the atomic mass made sense, but how they behaved in comparison to each other didn't make any sense. So it kept throwing the groups out of alignment. And this kept happening until Henry Moseley, who was actually not even a chemist, he was a physicist, someone who studies physics, he kind of really understood some of the work that Rutherford was doing with the atom, and he figured out that if we arranged the elements by atomic number instead of atomic mass, then the groups would fall into the expected order. So again, Henry Moseley proposed that we arrange the elements by atomic number instead of atomic mass. That's the changes he made to the periodic table. So the current periodic table that we use, the modern periodic table, is based on our knowledge of the atom. We now understand that energy levels and energy sublevels of atoms, remember that S, P, and D and F that we talked about, they're the reason for the repeating periodic arrangement of elements. So in science, the word periodic means repeated, regular intervals, regular patterns, so hence the name, the periodic table, because all of these elements behave similarly and that behavior repeats, and it's because of electron energy levels and sublevels. All right, so again, in science, periodic means repeated, regular intervals or patterns. So there are several things you're going to have to memorize about the modern periodic table. And I've already given you several copies. I'm going to give you yet another copy that we're going to do some things on that will help you to remember where all of these things are. Okay, so looking at the periodic table, there is a darkened black line, and it looks like steps. It's a zigzag line. That line divides the periodic table into a left side and a right side. All the metals on the periodic table are found on the left side of this jagged line. So where these red arrows are here, all of those are metals. So again, metals are found to the left of the jagged line. The left of the jagged line. Which means that on the right-hand side, these blue lines here represent where the non-metals are found. So they are found to the right of the jagged line. So let's do that again. Metals are found to the left of the black jagged line in the periodic table, whereas non-metals are found to the right of that same black jagged line. The metals that actually sit on this black jagged line, so the ones that are kind of pulled out for you right here, the ones that are highlighted in gray, have a special name called metalloids. So again, the elements that sit on this jagged line of the periodic table are called metalloids. Now when you look at the periodic table, you would realize that you have like two tall sections on the left, and then 6 tall sections over on the right, and then everything in the middle is kind of like shrunken down. Those metals in the middle are called transition metals. So the metals in the middle of the periodic table are called transition metals. I'm sorry that the picture is kind of weird right here. Don't know what caused that. But you would notice that the periodic table is divided or arranged into columns and into rows. Well, we give the columns a special name. So the columns in the periodic table are known as groups or families. So again, if it goes up and down, north to south, top to bottom, those are known as groups or families. And elements that are in the same group or family have similar physical and chemical properties because they have the same number of valence electrons. So remember, valence electrons are the electrons in the very last energy level of an atom. And if you think about it, members of your family probably look similar to each other, like people could look at you and figure out that you're related. So you guys have similar physical properties. You probably behave like some members of your family. Maybe you're more like your mom, or you're more like your dad, or maybe you're a mixture of both. So you kind of have the same chemical properties as well. Well, elements behave in the same way. Because they're part of the same family, they kind of look like each other, and they behave like each other. And the reason they do this is because of the number of valence electrons. They all have the same valence electrons. So again, don't forget your valence electrons are the electrons in the outer energy level of an atom. So the very last ring. So like in our examples, this would be our last ring, so there would be one valence. This would be our last ring, so there would be two valences. And that would be our last ring. There would be three valences. So how do we know how many valence electrons an element has by looking at the periodic table? Well, if you look at your periodic table just above the columns, you'd notice two sets of numbers. One number is just a whole number. It doesn't have any letters, and the other number has a letter. So like there's 15 or 5A, and then over here there's 16 or 6A. Well, those numbers, specifically the ones attached to A's or B's, they represent how many valence electrons is in that entire column. So again, this 6 means, this 6 right here, I'm doing a bad job of highlighting that, hold on. Let's try again. So this 6 means that every element underneath it has 6 valence electrons. This 5 means that every element beneath it has 5 valence electrons. So that's how you can tell. So really quick, look at your periodic table, or you can use the one that I have up here. I want you to tell me how many valence electrons are in oxygen, in chlorine, silicon, argon, silver, and magnesium. Some of them are on the one that's on the slide right now, but you may have to pull out your periodic table to figure out the rest. And I'll give you like a minute to do that. Okay, so your minute is up. I'm going to go ahead and move on to the next slide. Alright, so here are the numbers you should have come up with. I'm going to give you a couple of seconds to double check and see if yours are right. If you got anything wrong, then just go ahead and change it to the right answer. Okay, so we talked about Lewis dot structures in the last set of notes that you took. And again, a Lewis dot structure is just a way to represent how many valence electrons an element has. So you have 4 of them on your sheet: hydrogen, nitrogen, sulfur, and neon. Look at your periodic table and figure out, circle, which one is the correct Lewis dot structure. Give you like half a minute to do that one. Alright, so they're the right answers. Go ahead and circle the ones you got. Hopefully you got them all right. And if you didn't, then just scratch it out and circle the right one. So, there are several groups and families on the periodic table whose names are important and you need to remember them. And they are group 1, group 2, group 17, and group 18. Group 1, and these you're going to write these down for me. Group 1 is called the alkali metals. Group 2 is called the alkaline earth metals. So group 2, alkaline earth metals. And they are the first two columns in the periodic table, group 1 and group 2. Alkali metals and alkaline earth metals. Group 17 and 18 are the last two columns in the periodic table, so they're all the way on the other side, on the right-hand side. Group 17 is called the halogens. Some people say the halogens, same thing, halogens, halogens, it doesn't matter. And group 18 is called the noble gases. Noble gases. All right, so here you have 4 elements: oxygen, carbon, boron, and nitrogen. You're supposed to look at your periodic table and figure out what groups they went with. Oxygen is in group 16, carbon in group 14, boron 13, and nitrogen 15. So just like columns have special names on the periodic table, rows have special names as well. So a row is if you're going across from left to right or from west to east. A row on the periodic table is known as a period. So hopefully that's easy. And all of the elements in a period or a row have the same number of energy levels. So if they're all in period 1, they only have 1 energy level around the nucleus. If they are in period 2, they have 2 energy levels around the nucleus. If they are in period 3, 3 energy levels. 4, 4 energy levels. 5, 5 energy levels. You get the point. So the elements whose valence electrons are in S and P, remember we said S is one sublevel and P is the other. S can only hold 2 and P can hold 6. These are known as our representative elements. So which elements are filling their S and P sublevels are representative elements. And the number of the valence electrons of these elements are followed by an A. So that would be the first two columns. The first two columns of the periodic table, and then the last 6 columns of the periodic table. So the parts highlighted in blue and red for you. And again, they have their S and P orbitals or sublevels filled. The elements whose valence electrons are in D and F sublevels are known as transition elements. And the number of valence electrons of these elements are followed by a B. So those would be the elements in the middle that we talked about before. And then there are 2 small rows that are kind of pulled out to the bottom. They would be transition metals as well. So that's D and F. So the representative elements have their S and P sublevels filled, and the D and F sublevels are filled in the transition elements. Okay, this one you should know from when we did extensive properties and intensive properties. Remember us talking about iron, cobalt, and nickel, and we said that they were ferromagnetic, which meant that they could be made into magnets and were attracted by magnets themselves, and their special name was the iron triad. Not the iron trinidad, but the iron triad. Okay, group 18, or the noble gases, is a very special group on the periodic table. They're called inert gases. Inert just means they don't react. And it's because they have 8 valence electrons, and their S and P sublevels are filled. So they don't have a lot of reactions. They have the fewest reactions. So again, the group on the periodic table that undergoes the fewest reactions would be group 18. It is called the noble gases, and they're unreactive because they have 8 valence electrons and their S and P sublevels are full. All right, that's it for today's lecture. So you won't have one tonight because we did this one in class. And now I'm going to talk to you about our practice work before the bell rings.